Hello everyone, welcome to this video. My name is Sentinel-2. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate urban green space using Sentinel-2 images. Let's go to the Earth Engine code editor environment. In the first step, you need to set your region of interest. In this tutorial, I'm going to select a part of urban area in Iran. The capital of Iran, Tehran, is a metropolitan area. As you can see, here I have Tehran. You can do this tutorial for all around the world, all the cities in all around the world that is detectable using Sentinel-2 images can be used for this tutorial. For example, here I'm trying to do this tutorial for the Tehran. As you can see, lots of green spaces available here, and then through the labels, I'm gonna have remove the labels first to have a focus on green spaces that you can see in the Google image, and then you can select the part of the city and calculate the area and also the NDVI value, and then the area of the vegetation cover for that region specifically. For example, if you zoom in on a study area, here you can see that some green spaces available in different blocks, and then through the polygon tools available here, you can select some of the blocks that including vegetation cover. For example, I'm gonna select this region that's included vegetation cover inside the urban area like this. And then I'm trying to define the borders accurately. There it is. So after region of interest selected, you can zoom in more to see more detail for your region of the interest. So in the next step, in order to have focus on the study area, use map.center object geometry, just like that. Whenever you run the code, you will have a zoom or focus on your study area. Then we need a variable to assign Sentinel-2 images with. And here I have a new variable as Sentinel-2 equals to, through the search places and dataset, just type Sentinel-2. Sentinel-2 collection 1 level C and collection 2 level A, both of them available. Level 2A is the first choice for NDVI analysis. As I'm gonna use NDVI in this tutorial, I need to choose the satellite images with the that is atmospherically corrected. And also level 2A data atmospherically corrected and geometrically is also corrected, and it is the best option for spectral indices. Import it into the code and then assign it to the Sentinel-2 as a new image collection. Then we need to define filter bound and filter date to bound our data to a specific region. That filter bound first, I'm bounding the data to the region of the interest. This is a very important filter for the mid-resolution satellite data such as Sentinel-2 and Landsat 8 because of their framing structure. Then through the dot filter date, you need to expand your data to a specific period of time, for example from 2017 to 2024. As you can see in the dataset description, this data is available since 2017. Although Sentinel-2 launched in 2015, but and also some of its data is available from there in level 1C product, but level 2A product data is available since 2017, and then you can call this data into your code since the start date mentioned here. So now I'm gonna call this data from 2018, for example, to 2024. As I'm producing this tutorial in 2024, my maximum end date is 24. So for the next step, I need to make a variable that's I need to define a new filter that filter all the data based on the cloud cover. But before then, we need to get a print to see that how many data from Sentinel-2 is available for the selected region. For this region, the time span, as you can see, 363 element is available, and each image including 23 bands. You can have an overview about the band situation, band number 1 to the other bands available here. For the NDVI analysis, the near infrared band equals to band number 8, and the red band equals to band number 4. The band number 8 and 4, both of them offering 10-meter spatial resolution and allowing us to get NDVI images with 10-meter spatial resolution for all around the world, specifically the urban area. As you know, the urban area is a really heterogeneous region and including different land covers and different things, and also it's a mix of different land covers, and also it's very difficult to differentiate some of the land covers. And also that's why we need to have a good spatial resolution as much as possible in the open source data to be able to detect the vegetation cover very well with a good accuracy. And when I'm making this tutorial, for now Sentinel-2 images with 10-meter spatial resolution is the best option for the urban studies, specifically for the vegetation monitoring. So, and then for the next step, we need to check in the properties available here. But before that, we need to open up the features and then go to the properties. As you can see, different properties available for each element separately. And one of the important parameters here we have is about the cloudy pixel percentage. As I want to monitor the vegetation cover, it's very important to have a cloud-free images. That's why I need to filter data based on 10% threshold in cloud cover situation. So now make a new filter for the cloud cover, Earth Engine. That filter Earth Engine dot filter dot lt less than. I need those of images in which the cloud pixel percentage is less than. LT means less than 10%. Run the code, and then as you can see, we have only 160 elements for the period of time in which the cloudy pixel percentage is less than 10. And so in the next step, I can do the further analysis such as NDVI calculation to get information about the vegetation cover for each date separately. So we need to make a loop that calculate the NDVI for each one of the elements available here. So to make a loop in the Earth Engine, just you need to use map function. In order to have a better view to the codes I'm writing, I make a more zoom here for you. That map, make a new function for a single calculation. Each input image from Sentinel-2 considered as an IMG in the loop structure. And now in the first step, I need to call a multispectral bands, as you can see, from band starting with B, 1, 2, 3, 4, and the other bands. I need to call the bands first and then apply the scale factor that its information already available in the data descriptions. If you go to the bands, you can see that some of the bands like band number 2, 3, 4, and 8, or the same as the other bands, have a scale factor that should be applied before any further analysis. It is this value, and then copy and paste it into your code. Make a new variable first, for example, as bands equals to, from input image, I'm gonna select those of bands starting with B and the rest of the letters not important, and then all of them multiplied to the scale factor value, just like that. The next step, make a new variable as an NDVI, and the corrected bands calling here into a near variable through the dot normalized difference, we can get normalized relationship between near infrared and red region. The near infrared band is here band number 8, and the red band is band number 4. If you back to the data description, you will see that band number 4 is located in 600 meter. That is exactly exactly matched with the red portion of electromagnetic spectrum, and also the band number 8 with 10 meter spatial resolution and 800 nanometer spectral wavelengths. It's a good option for as a proxy for the near infrared region of electromagnetic spectrum. That's why we are using this combination for the NDVI in the Sentinel-2 images. Through the dot rename, you will be able to change the name from the default name to the NDVI or any other name you prefer for your study. Then finally, function returning the NDVI images with some of the properties of input images. One of the main important properties that we need for the time series analysis is about system time start and system time end. System time end that is necessary for the time series analysis in the Google Earth Engine platform. Run the code again, and now again there is 160 band here, 60 image here, and also for each date we have a band including NDVI with system time start and system time end information. So the NDVI images gets ready, and in the next step I'm gonna show you how we can visualize the vegetation covers in the urban area. So for the next, we need to make an average image first, and then try to calculate the average area of vegetation cover. That's what I'm gonna do in the next step. A new variable as NDVI average or NDVI mean equals to, from Sentinel-2 images, I'm gonna calculate the average value in each pixel. Instead of having average, I'm trying with a median. The median is same as mean, but the main difference is the median ignores the extreme high and low values in the time series and prepare and offer a more accurate average about the situation of the region you are working. Then through the map.add layer, I will show you how NDVI means, what kind of information included by NDVI mean. NDVI mean clipped by region of interest that is already named as a geometry, and the visual properties leave it empty first, and the layer name here should be NDVI average or NDVI mean, and use the false in this step because it enables this platform show the final result immediately, and also you can visualize it whenever you want. So save your code and run it again. We have focused on the region of interest by the center object, and now NDVI average is calculated in the layer setting. Click on NDVI average, and now you will see the average NDVI calculated in each pixel. That is a grayscale image. As you can see, it is a grayscale image from black to white. The black region, lower NDVI values showing with black color, and higher NDVI values showing with white, showing in white region. And as you can see, the white region, all of them showing the vegetation covers in the urban area. So if I have a little bit more, if I have a little bit zoom on the study area, you will see that the white region completely exactly matched with the green spaces we have in the Tehran cities for specific blocks that I have selected. So here, for example, using some of the tools we have for the transparency, If I have more zoom here, that's what it looks like. The background high resolution image enables us to see the vegetation covers easily and even some of the trees available alongside the streets. And now image is loading. I'm waiting to see the final image. You will see that the green spaces exactly correspond to the white regions in the Sentinel images, and also alongside the cities, if you can see the bright pixels, it's a reflectance of some of the trees that we have alongside the roads. But remember that the background has, for example, 3 or 4 meter spatial resolution, and also the foreground Sentinel-2 has 10 meter spatial resolution, and definitely we will have some differences between the foreground and background. That is because of the difference in spatial resolution. So as you can see here, for example, these regions with vegetation cover, you will see that the higher NDVI values, and also the vegetation covers alongside the city, as you can see here, reflected very well. This region specifically reflected the green spaces we have, trees alongside the roads and streets. So now, after you get understanding about the situation of the green space in the blocks I have selected, and also if you get information about the NDVI values, now through the inspector I'm gonna show you the range of the values that we have in this place. But before then, if you want to get information about the whole range of values for the selected region, you can use the histogram. Print user interface chart image.histogram. As you can see, a couple of arguments available here. The NDVI image, and the average one is the image I want to get the histogram for the selected region as a geometry, and the scale equals to the temporal scale equals to the spatial resolution. And now you can get rid of the rest of the arguments we have here. Run the code, and in the right panel we have a console. In the console, a new chart is under generating. As you can see, this is a chart, this is a histogram that's showing the frequency of NDVI values, starting from minimum NDVI we have in our study area to the maximum value we have in our study area for the NDVI values. And now you can see that most of the pixels have NDVI around the 0, because this is an urban area, and the dominant the dominant cover is the buildings, and also the buildings and soil have NDVI around, including NDVI around 0. And also, as you can see, we don't have any negative values in this region except some minor values. But this is not related to the water content, because we don't have the water content in this area. That's why most of the values are starting from the 0, or the negative values are really close to the 0. That's why, because we don't have the water cover in this region. And also the values above 0.2 or 0.3, mostly including the vegetation cover and corresponding to the vegetation cover in our study area. So now check NDVI mean again, and also have a focus more on your study area to check the values on the image to get better understanding about the histogram of NDVI for your region. Using a stretching technique, you can increase the contrast in the image. Yes, now that's what it looks like. Through the inspector, if you click on the white region, you can see that, for example, the value is 0.6, and another region is 0.5, and another one 0.5 again. It's showing that the vegetation covers mostly including values greater than 0.2 or something like that. Yes, definitely values greater than 0.2 or 0.25 could be a good threshold to differentiate the green space from non-green space pixels in these images. So now I'm going to show you how we can calculate the area of urban green space in this tutorial. Just make a new variable first as a threshold. This is the NDVI threshold value equals to from NDVI mean. I need to select those of pixels greater than 0.25. Yes. Now I will have a binary image with two kind of values, 0 and 1. 1 equals to the vegetation cover and 0 equals to the non-vegetation cover. Through the map.add layer, you can have a sense, you can get information about the output after setting a threshold. So here I have the NDVI threshold that is clipped based on the geometry, and then I leave the visualization parameter empty, and here the name is NDVI threshold, and the spatial resolution, and no need to a spatial resolution, just use the false to avoid automatic visualization. So code is running again. Now we have an NDVI threshold image. If I click it, if I check it on, you can see that we have a binary image, black and white regions. The white regions showing the vegetation cover, pixels greater than 0.25, and also the black regions showing the non-vegetation cover area. As you can see, that's what it looks like. It's almost very good discriminated the vegetation cover from the rest of the pixels and the rest of the covers that is detectable in the Sentinel-2 imagery. But before to calculate the area of vegetation cover over the urban area, we need to get rid of the zero values in our calculation. To do this, I need to make a mask in this step. Here, another variable. Here we have NDVI mask equals to, in order to get rid of the dark region, here I'm masking the NDVI threshold based on NDVI threshold. Because update mask is a function helping me to get rid of the black regions. So copy map.add layer again, paste it, and here NDVI mask, clip it based on the region of interest, and instead of the NDVI threshold, here we have NDVI mask. Run the code again, and now you can see the NDVI mask is ready, and the only thing here we have is actually the vegetation covers that is showing that the region correspond to the real vegetation covers that we have in the high resolution images. And also this visual comparison give you a good insight about the threshold you need to set to detect the vegetation cover and separate it from the other phenomena that you have in the urban area. So after we get rid of the darker region or zero value or undefined values, now we can calculate the area of each white pixels you can see here. Now make a new variable as NDVI area equals to, now the white pixels including a value number 1. For example, through the inspector, if you click on each pixel, you will see that the NDVI mask including only values number 1. So now I'm gonna convert the value number 1 to the area of each pixel. How to do this? It's very simple. Get from NDVI mask.multiply Earth engine image pixel area. Actually, the pixel area is a function allowing us to get the area of each pixel separately, and then in order to convert it from a square meter to a square kilometer, just you need to multiply it to you need to divide it to 1 million. Divide to 1 million. 1 is 6, is a constant value for conversion from a square meter to a square kilometer. So now again, map.add layer, repeat it again, this time for NDVI area, NDVI instead of NDVI mask, we will have the NDVI area. Run the code again. So here, visually nothing changed. Still we have the white pixels, and also it is correspond to the vegetation covers. The only thing changed is about the value of the pixels. If I click on the pixels values, now you can see that it is including the area of each pixel and also with a square kilometer. So now I need to get the sum of the area, pixels area, to reach to the final area for the whole vegetation cover that I have in these blocks. So to do this, it's very simple. Here we have NDVI, we have area value equals to get NDVI area first. Reducer.sum is a function allowing us to get the sum of the pixel values, that here is the area of each pixel, to find the total area of vegetation cover for this region. NDVI area dot reduce region. The reduce region. So now the reducer is Earth Engine dot reducer dot sum. Get the sum of the each pixels, and the geometry or region of the interest equals to the geometry, and the scale or spatial resolution should be equals to 10 meter, because we have a spatial resolution as 10 meter. And now to have the area as a single values, use that values and then get the first item here. And now I'm printing the area value at the end. Code is running in the console, a new object is under calculation. So if you want to convert this object from the object structure to the number structure, it's very easy that you can do by Earth Engine.number. The total area of vegetation cover is 0.6 square kilometer in this region. If I remove the conversion from a square meter to a square kilometer, finally we will have the area in a square meter. As you can see, the area is this number. The area of vegetation cover is this number according to the square meter. And now you can change your area and also get the area of vegetation cover for different regions. So in the next step, I'm going to show you how to do this procedure with the time series, because in some of the projects you need to know that how much NDVI, how much vegetation cover changes in your study area. It's very easy to use, and also it's easily done in the Earth Engine because of the applicable functions available in this platform. So the main variable including the NDVI is Sentinel-2. The only thing we need is make another loop and repeat the whole of processing step inside the loop to get the area values from one time to another time based on available images we have. So now I'm making a new variable as NDVI as urban, or for example we can say the tree area equals to, if all of the NDVI value is related to the tree, we can say the tree area. This is an example. So equals to get Sentinel-2 images first. It is including the NDVI value. As you can see, NDVI already calculated in this variable, and the only thing we need to do is apply this threshold, use the threshold, mask, and area inside the function. So here, make a loop using the map, and here we have a function. Each input image considered as an IMG, each input NDVI considered as an IMG, and now in the body, first we need to apply the NDVI threshold. Just copy and paste it into your code. Here, the first variable, the NDVI threshold. The next variable is masking process. Just copy and paste it as a next variable. So in the next step, we need to calculate the area of each pixel using a square meter. So, and now the NDVI area is also calculated. Finally, the function returning the NDVI area for each date. We have image. The NDVI area returning with the properties of input images. That is very important to have the properties for the next step, because in the previous step we had a one image and also we calculated the area for that single image. But here I want to calculate the area of each single area of vegetation cover in each image separately and plot it simultaneously. So to do it, I need to make a chart. Chart image.series is a function helping me to do this procedure very well. Here, print user interface chart image.series. We have a couple of arguments here. Instead of image collection, I have the tree area and the region in which I'm gonna get the area of each pixel. Area of vegetation cover is actually the geometry, and the reducer is very important. As you know, we need to get some of the areas, the sum of the vegetation areas for each date. That is important to set the reducer as sum, the same as the previous example. So Earth Engine .reducer.sum. Here I'm using that sum, and the scale should be 10 because the spatial resolution is 10, and the X property should be equal to the system time start. Actually, the system time starts including the data acquisition for each image and helping us to plot the data for each date we have image. So now you can see that a new chart is under generation that will show the area of vegetation cover for each date. So I'm waiting for the new image, for the new plot. So maybe something is wrong in the function, and also we need to check it out to see what's the problem. The problem here, back to the NDVI mean we have here. Actually, we have a function that each input image named as an IMG, and we need to get to set a threshold from each input image that is IMG here, not NDVI mean. That is the big problem I had. It was my mistake, sorry for that. And now you can see that the variation of the vegetation cover is plotted here. But for some of the times, for example, the cold season, as you can see, we have a dropped value. The area values dropped. It is related to the NDVI threshold values. As you can see, in the winter time, the amount of vegetation cover, the amount of chlorophyll decreased in the vegetation cover. That's why we cannot detect the vegetation covers very well, because these are not evergreen. The trees and also the leaves in this region, the vegetation covers not evergreen. And also that's why in the winter and also the cold season we have lower values, and because the chlorophyll content decreased and NDVI value also decreased and get close to the zero. Now to solve this issue, we can filter out data based on the season. For example, here I can make a new filter, that filter Earth Engine, that filter dot calendar range. Based on the calendar range, I can set a period of time, for example, from June to September or to August. I can select images only for a specific months. And here the filter is months, and the code is running in the right panel. Again, you will see a new chart is generating, and yes, there it is. And now the variations is also totally true. Because, and also if the figure of the plot is not very interesting, you can change it using the set chart type. Here I'm changing the chart type from line chart to the column chart, just like that, and helping you to get more better understanding about the variation of the vegetation cover area for your study, for the region of for the region of interest you are working based on. And if you want to get the CSV file, here download CSV, helping you to get the Excel file for the further analysis if you need it. And that was the tutorial that I showed you how to use Sentinel-2 images for urban area green spaces. And I hope you liked this tutorial as much as I did. And also, if you had any question, please put your comment in my YouTube channel. And also the code also is available below the video in my YouTube channel. There is a link for the code, and also you can compare yours with mine. And if you had any problem, you can share it with me. And I hope and also you have a good time, and thank you for your attention.